Hey guys, so as I promised yesterday, um, this is the new piece of equipment from good old HP. Actually, you can't even see the badge anymore, but trust me, this is an HP. It's a 4145 semiconductor parameter analyzer, and it's about from 1982. And have a listen. I double dare you find a better sounding piece of equipment booting up. Um, it's got this nice cathode ray screen here for the interface. A glorious, full, like everything you could ever need to um, input into the device is here, laid out very nice and convenient. And it's got quite a lot of interesting things. Like you could see that if you hit, I think shift and shift and electron, for example, the electron charge, and say execute, you're gonna see 160.2 times e to the negative 21st. So it has all the constants you'd ever need for designing transistors and characterizing them and extracting all the information that this thing can do. So I've told you about the front panel, I've told you about the device itself, but what actually is this thing? So when you make a semiconductor, basically a transistor, a diode, a JFET, or anything else like that, a semiconductor, you want to first design it and simulate it, or actually in the old days they would actually simulate it on paper, basically math it out. And then you would send it to the foundry, which would return you a wafer, a silicon wafer, filled with test chips or test components, basically. So then you would actually take one of these, connect it to that piece of silicon that you designed, and characterize it. And you would correlate the results from the measurements, which you would trust this thing absolutely, and the simulation, and see what you need to tune in order to get in order to get your finished product. I'm still hitting shift. I want to set the auto. It has an auto cal button which lights up saying that it needs to do a self-calibration when it first boots up. So this thing would originally come with a big floppy disk drive with quite a lot of information it actually needs to boot. So it's continuously running stuff off of the disk drive and writing it back. And instead of having a floppy disk drive, the one I got from eBay actually has a floppy emulator with an SD card. Okay, so I have a quick demo set on this thing, so I'm just gonna next through it like crazy, and then we'll go back into a more detailed description of what's going on. And just in very short, what's going on here is we're drawing the characteristics of a basically an NPN transistor. So you can see we have the three regions of the transistor's operation basically graphed out. This is the linear region, this is saturation, and right here is it being off, right? So turned off. Linear region means that it satisfies the collector current is equal to the base current times the beta of the transistor, the HFE, the gain. Saturation means that it's basically a wire. It's as the collector emitter voltage is as low as it can possibly go. And off means that the transistor is basically not conducting anything. So this uses devices called source meters, source measure units. And this is a great segue to show you even more of my gear acquisition syndrome And the next thing I'm going to show you to give a bit more clarity is a source meter, a source measure unit. The one I've talked about previously, but I didn't explain much about. So, we'll get back to the transistor and why this thing is so amazingly awesome. But first of all, let's get back to slightly older, slightly more interesting technology on one side, but slightly less flexible. Okay, let me move things around and I'll be right back. Okay, so this is my lovely 236 source meter. It's made by Keithley, as it says here, bright and red and pretty. This is from the brown shoebox era, and this is basically a glorified power supply with some extra smarts inside. So if we turn it on, you'll be able to hear that it's also very loud and has a very big, like, mains voltage fan inside. It's actually very weird. The fan inside here runs off a separate 110 volt tap from the transformer. So it's part of the reason why these things need a very particular fuse rating in order to work on 240 volts. If you get the wrong kind of fuse, I'll link the one I found which always works on this one. If you get the wrong kind of fuse inside, it will always trip, always pop, and basically you need to swap out the fuse every time you turn on the device. So what is this thing? Let's take a look. So we have operate, source, and measure. Source means what the power supply is doing, and measure means what result it's returning to you, what is actually being measured. And we have source V and measure I, which means it's going to act to the best of its abilities as an ideal voltage source and measure the current being drawn by the device under test, but to a very, very good degree. So this is like a 5.5 digit multimeter. Newer ones, like the 2400 series or the 2450 series from Keithley, actually have 6.5 digits, and they're much more, let's say, up to date with modern standards of measurement, and they have many more bells and whistles. But this thing is still remarkable in its performance. So if we go to compliance, you can actually see compliance is basically the current limiting or the voltage limiting. You can actually set a compliance current to the nearest 100 femtoamps. So this is going to be a picoamp, 100 femtoamps. It also can go up to basically 100 milliamps maximum at 110 volts. So in this configuration, it will output whatever voltage I tell it to output, and it will measure the current being drawn by the device. There's nothing plugged into it right now, but we can just turn it on and operate and look a bit at the readings. So we can see we have 1, 2, 3, 4, 5 digits. So 5 digits or 4.5, whatever you want to call it. And the measuring range is adjustable. You can set it. Moreover, you can, in order to get good readings on both the voltage and the current, it has quite a few ranges. So it has a 1.1 volt range, a 10 volt range, and a 100 volt range, and then it goes down a lot more. Like the smallest range, I think it's 1 volt. So you could set a voltage to 1 volt and measure 100 microvolts. Yeah. So what is this thing capable of doing? Well, for example, you can just basically power up a semiconductor or a device and measure the current it's using very accurately. Or you could sink power from a device, like you're testing a power supply and you want to characterize it very carefully, or you have a low voltage, low power LDO, low dropout regulator, and you want to characterize it. You can sink power into the device like an active load, and it will dissipate it internally. And you can also set the function in DC or sweep. Sweep is the one we'll be looking at right now. And in order to show you what sweep does, we're gonna have to start up a bit of software on the computer and do some screwing around there. So sweep basically means that it's gonna apply either a current or a voltage sweep, any type of sweep, so linear, logarithmic, or any random thing, and it's going to measure the current for each step, or vice versa. So it basically characterizes a device over a very broad range of currents or voltages. Okay, give me a second to set things up and we'll talk about that. Okay, so what I've done here is I've connected a diode to the output of the source meter. And I'm gonna go to this piece of software that I have here, which is made by a very nice guy. I would show you the about, but I'm just going to link it in the video description. So this is a specific piece of software made for the 200 series and 2400 series source meters from Keithley, and it's made to make them easier to control. So these older Keithley source meters actually have a very rudimentary GPIB language. So they don't really understand modern commands. They had such small amounts of RAM and such limited resources that, from what I understood, their internal language was called R2D2 because it was full of just backslashes and ampersands and stuff like that. So what are we going to do? We're going to first of all do a diode sweep, and we're going to go from, let's say, a nanoamp to a milliamp or 10 milliamps. Let's leave it as that. And where are we going to go like this? It's a it's going to take it's going to source several currents. It's going to source 10 points per decade, so 10 points per scale, and measure the voltage across the diode. What's going to happen when we're going to do this is that we're going to see the characteristic of a diode. And right now you can see it's measuring, it's sourcing and measuring, and you can see the characteristic looking IV diagram of a diode. So we have the forward voltage of around 600 millivolts, and the slope of this graph here is basically the equivalent resistance of the diode. So if it was an ideal diode, the slope would be perpendicular to the voltage axis, basically to the x-axis. But since nothing is equal, the diode isn't behaving ideally, and it has a certain slope to it. What happens if we plot it on a log scale? Well, you can see that the behavior of the diode is perfectly logarithmic, actually exponential. So the current through the diode increases exponentially with the voltage, and that's due to basically the semiconductor behavior. I'm going to link a paragraph about the equations behind this in the description. Okay, we have a silicon diode, and a pretty good one. This is a pretty high power diode here. Let's see a germanium diode. Okay, so I cheated a bit, but I'll run it again so you can see the display. Nanoamps, microamps, etc., etc. And we have a nice graph drawn again, and you can see this time that the forward voltage of the diode is much smaller, as is tradition with germanium. Germanium diodes usually have a much smaller forward voltage than silicon diodes, and it's around 200-300 millivolts. And that's the same actually for transistors. The base emitter voltage for a silicon transistor is 0.6 volts-ish. For a germanium transistor, it's 0.3 volts. So you can see the slope is much gentler. So the resistance of this diode, the equivalent resistance of this diode is much worse than the previous one. And you can actually see the same exponential behavior in current but we are going into basically the noise of the instrument here. So we're very close to zero, and yeah. Okay, what else can you do with this source meter? Well, let me get a couple of more examples, and we shall discuss a bit further. So what you saw me just enter in the data here is basically, this is a source current measure voltage operation, and it's going to do a linear sweep from negative 100 microamps to positive 100 microamps, and it's going to do 100 points. So if we hit execute and wait for it a bit, we can see that we have drawn a flat line, and it corresponds perfectly because this is a resistor. So a resistor satisfies Ohm's law, and Ohm's law says that current through a resistor is equal to voltage divided by the resistance, and we can actually calculate the resistance. And you better believe me when I tell you that it's about 50K. And as any good resistor would behave, the current through the resistor at 0 volts is about 0. If this was any sort of magic component, the current at 0 wouldn't have been 0. Okay, and one more thing we can do using this, but it's not the proper way to demonstrate it, is we can connect a capacitor to a source meter, and because this thing goes up to very small currents, we can do leakage measurements in the dielectrics of capacitors. So if I tell it to go to local first and set it to output, I don't know, let's say 5 volts, and we go to the smallest measurement range. Let's go to nanoamp. I think it's gonna clip. Okay. And then if we say operate, it's gonna hit compliance for a bit. Sorry, just a second. And you see that it's saying that it's in compliance, so it's probably a lot leakier than that. And now that the capacitor is charged, we can see there is some leakage in it. Anyway, the setup isn't very ideal because we have a lot of leakage paths around, and although this is a triax cable, it's not the best, and it's not in a very shielded box. So we can see that if this is a nanoamp, we got, I don't know, less than 100 picoamps of leakage through the capacitor, which for long leads outside exposed, you know, that's pretty decent. I'd call it decent. We can go to a longer integration time, so we can stabilize the readings a bit, and we can even apply a filter, but you can see it's about, right now it's about 5 picoamps of leakage. So the dielectric in the capacitor is basically leaking some current. At 5 volts, it's leaking about 5 picoamps. If we go higher, the leakage would be progressively worse until the dielectric breaks down and the capacitor becomes a short circuit. Okay, so I've shown you all about this glorious piece of equipment here, and you can see that for longer integration times we get an extra digit in the current reading. So I've shown you this glorious piece of equipment here, and I've demoed it even better, I might say, than somebody else who made a video about hot rodding one of these from a 236 to a 237. Wink wink. Why have I brought it up in the first place? So the 4145 that I've been talking about is actually 4 of these in one box. I know, crazy, right? It's like 4 times as many components. I'm joking. It's 4 times as awesome at least. So let's get back to the semiconductor analyzer. We'll talk a bit more about that, and then I'm going to show you how you would go about characterizing an NPN transistor, and we'll try a MOSFET if I can find any easily. So this is all about, that's all about the source measure units and what you can do with them. I'm sure there's many more applications than what I've shown because I haven't shown you the 4-quadrant operation of this device. But I hope it's been educational and a good build up to the next thing. So I'm gonna turn this off. I'm gonna connect the cables back, and I'm going to show you how you set up a transistor analysis on the semiconductor parameter analyzer. Be right back. Oh, by the way, Mr. Reps, I'm sorry. Never meant to say that I was any better than you at showing anything. Everybody knows you're the Keithley expert on YouTube, so yeah. It's because of him that I bought this thing. So you go buy some, thank him, and do awesome stuff with it. Alrighty, so I'm back in this main menu here. And we have basically the operational sequence of the device here. So we have the channel definition, which means what channel you assign to what function, source setup, measurement display mode setup, auto sequencing setup, and output sequence setup. Let's go through them one by one and arrange the thing to work for characterizing a basic, basic, I said first, an NPN transistor. So the first thing we do is go into the channel definition, and we see that we have some options preset here. So we're going to go to transistor VC, collector emitter voltage, and collector current. And we see that SMU1 is the common. That's basically the ground. SMU2 is the base voltage, and it's measuring a base current. SMU3 is collector emitter voltage, and it's measuring collector current. But you can see it's actually sourcing current, and this one is sourcing voltage, and they're measuring their corollary. So if you source current, you measure voltage, and you source voltage, you measure current. So we agree with this completely, entirely. They know much more about what they're doing than us. Next, collector emitter voltage topping out at around a volt, and 10 millivolt steps, 101 steps, and compliance current 100 milliamps. That's very good. Base current and 5 steps from 10 microamps to basically 50 microamps, and a compliance voltage for the current supply of around 2 volts. And that's it. Next, we want to display collector emitter voltage on the x-axis linear, and on the y-axis we want to display a collector current. And the 5 different characteristics that we're going to see are derived from the 5 different base currents. Okay, we hit next, and we're brought to the graphics display, and we have to set the device to measure. Measuring light lights up, and we can see it starts drawing. And we definitely screwed something up in the graphics because we need to hit auto scale. And it's done an excellent job of auto scaling things very nicely, so we can get the full information, the full kit and caboodle. And we have a peak current of around 2 point something milliamps. We can actually enable the radicals, so 2 almost 9 milliamps collector current for the most base current at VC of around 0.3 volts. So if you're a hardcore analog designer and you're designing, for example, a matched differential amplifier with transistors, you need matched transistors. So you'd characterize a bunch of transistors until you find 2 that have very similar looking characteristics. So this is about everything I can show you on this device right now. I didn't find a small signal MOSFET, and I'm fresh out of JFET since that Stanford Research repair. Oh, by the way, I don't have that thing anymore. I had to give it back, and it was scrapped. I had to know it, you had to know it, you have to share my pain. Okay, so we are going to look at one more thing, because this thing is still lying a bit to us. It's hiding some crucial information, and it's got something to do with the early effect. Give me a few seconds to reconfigure this whole spiel here, and we're gonna go and look a bit deeper into the actual workings of a transistor. So I'm going to go previous, and I'm going to increase the stop voltage to around 15 volts. Actually, wait a second, I'll be right back. Okay, so if we go back here, we're gonna see that I changed the voltage up a bit more. I'm actually gonna go up even higher. I'm gonna go to 40 volts, which is the most that this thing will actually let me run without the fixture. And I'm going to set the top of the scale to the top of the x-axis to be at 40 volts, and then we're gonna hit measure and wait for it. Actually, I'm gonna short it up to see it draw a bit faster. And it said that buffer is full. Anyway, let's change back to fewer points, 0.4, enter, and this should yield like this. It's got a very small buffer, so you can't store that many readings. And if you go single again, you're going to see something very interesting. If you look closely, and I hope you're going to be able to see, the linear region isn't behaving as it should. The current is increasing as you apply more collector voltage across the transistor. If it's in this linear region, the collector current is going to actually increase, which is not correct. If you look at transistor ideally, its collector current should be just a function of its base current. Like a bipolar transistor is basically an ideal current amplifier. As much current as you put into the base, you multiply it by its HFE, and you get the collector current. But that's not entirely true. The more voltage you apply across the collector and emitter of a transistor, the base gets smaller and the gain of the transistor gets larger. This is known as the early effect. It's basically as the more voltage you apply across a transistor, the better it becomes at being a transistor. And if we go back all the way back, and go back to the characteristics that we drew previously and hit run again. I just want to do that so you can see where I'm going at. They look flat here, but they still aren't flat. If you look very closely and you need the ruler to measure, you're going to see that these flat lines actually meet, all of them meet way behind zero. And they all meet at a specific point, which in an ideal transistor is actually infinity, but in a regular transistor it's called the early voltage. So that's about it for transistors. This is the most awesome piece of equipment that I own. It's extremely powerful, especially for its age. This was made in the 1980s, if you can imagine that, like revision 1982 or something like that. And it's still incredibly expensive to this day. I was very lucky to get this one, even with the SD card mod and everything, for the price that I got it for, because they still sell for a couple of grand on eBay. Mind you, I didn't pay that much for it, and I don't think it's worth what other people are asking for it. But I got it for around 500 bucks. Actually had to ship it from Italy to Germany to a friend of mine, and back from Germany to Romania because the Italian ship sender didn't find a freight service that would pick this thing up. It's 35 kilos and it's almost 80 centimeters long, so that way. I'm not going to show you any more of it because I'm planning on doing a teardown of the thing, so showing you everything that's inside important. So the source measure units, the voltage sources, and the voltage monitors, because it's not only 4 times as awesome as the 236, it's more awesome. It has an extra 2 voltage sources, and it's got an extra 2 voltage monitors. All right, and hopefully by that time the fixture will come, and I'll be able to demo the whole thing as it came from the factory. So this thing usually had a fixture that you could plug different footprints in, basically different packages in, and then you'd plug your components in and have match between 2 halves of a JFET, measure the mismatch between 2 halves of a JFET, or select JFETs to match, or select transistors to match, or MOSFETs, or even diodes if you cared. And you could do all sorts of analysis. You can even control it through GPIB, or as it's quaintly called by HP, HPIB, because they invented the standard, evidently. Hewlett-Packard Interface Bus, that's what it used to be called. We're gonna take a look inside. We're gonna see how it works. It's absolutely massive, and it's bench dominating. It's making a lot of heat at the moment, and it's already summer here, and today it's been like 30 something degrees out, and this thing has made the entire room noticeably warmer in the short time it's been on. So I'm gonna turn it off. I'm going to let you hear the fan unwind, and I'm going to thank you for watching and hope to see you on the next video.